changed my computer because I have not been retired yet. I have no time to prepare the slides. So my student prepared this presentation. Sometimes Japanese character included in this computer, in this presentation. That's why I use my note PC. So today I will talk the two topics shown here: the evaluation of and the visualization of stress and strain state under non-proportional loading. Okay, so I think that all of you already know that under non-proportional loading, strain-controlled non-proportional loading, so additional hardening due to non-proportional loading occurs, and also we can see the drastic reduction in failure life due to non-proportional loading. So this additional hardening and the reduction in failure life depend on the material, not only material, but also loading path. So therefore, in non-proportional loading, evaluation of stress and strain and non-proportionality is very important to evaluate the failure life. So in multi-action loading, as you know, you use Mises or Tresca equivalent stress or strain. So in proportional loading, this is okay. So as you know, Mises and Tresca stress and strain always takes positive value, no negative values. So in that case, in proportional loading is okay. In the tension loading, we put a sign plus, and compression loading, we put a sign minus. That's very easy. However, in non-proportional loading, for example, for circular loading in epsilon and gamma, this is the axial strain, the shear strain, is the circular loading. So in that case, Mises equivalent strain is constant. How do we evaluate the strain range? Some researcher and engineer mistake. So if they use every finite element analysis, it takes always the same value. The stress range test has zero. This is a big mistake. And also in the random loading, in non-proportional loading, we must analyze the 6 components of stress and strain. It's very complicated. So there are several open questions. How to evaluate the stress strain and the non-proportionality, how to calculate stress and strain, and how to evaluate the failure life. And also how to describe them. Because as I told you, so many researchers and engineers are not familiar with non-proportional fatigue. So some researcher and many researcher and engineer does not know how to evaluate. So in this presentation, I will show one example how to show the non-proportional loading. So this is the contents in my presentation. The first read, I showed a simple method of determining the stress strain and non-proportionality, which called the IS method. I is my name, the S is Professor Sakane, is sitting there. And also showed the visuality presenting the principal stress and strain and non-proportionality. And also I will show quickly the life evaluation and the non-proportional random loadings. This is the first one, how to evaluate the stress strain and the non-proportional loading. So there are the 3 steps here. In the first step, after we obtain the stress or strain as a function of the time, we evaluate the stress and strain. In this slide, S means the stress over strain. At each time, we choose the maximum amplitude of stress over strain. This is SIT. And in one cycle, in the full cycle, there the maximum one. It takes we take the SI max as a maximum. Okay. That's it. So I mean that we always evaluate the maximum amplitude of stress over strain. And second one, we must evaluate the direction of principal stress and strain at each time. So in this coordinate, the x is this is the I call the reference axis. So maximum SI max direction is set into this direction here. And at each time the stress vector is changed and moved like this. And so this direction, how to determine this direction? We always monitoring the maximum direction of stress over strain, not absolute, maximum. So we always maximum direction of principal stress strain, and we can obtain the vector at time t. And this angle, so please remind you that this is the half of the xi. This is the angle, and also the projection of this vector onto the yz plane, and between the y-axis and the projection, the vector, this angle, the zeta, the second angle, and then we can in equation we can calculate the two angles using this equation. This is the second step. And the third one, we figure out the stress over strain first in the polar figure using the amplitude of stress over strain and the two angles, xi and zeta here. In this study, I employ the principal stress over strain, but of course you can choose equivalent stress over strain, stress equivalent ones. Anyone is okay. And also this reference axis direction, you can also choose any plane, any direction. For example, you can use a critical plane approach. Any approach model is okay. You can choose one direction using your theories. I skipped here. In the previous work, I proposed a non-proportional strain equated to this equation in the strain control test. It is very simple. This alpha is a material constant related to the additional hardening due to non-proportional loading. This alpha is dependent on the crystal structure. For example, for FCC materials, this additional hardening and this alpha in this equation is the same value. However, for BCC materials, so this alpha is a little bit different. For example, this is the comparison of the alpha. This alpha is evaluated from additional hardening. This alpha star is obtained from the data fitting between the proportional and non-proportional. And you see the FCC and BCC is different line here, using the several material right here. And then finally, I also propose this equation to evaluate the media line. under strain control test. And also, this part is alpha, and put a sign as this alpha star here. And also, we could also know that this alpha could be evaluated from the tension test. So sigma V is strength, and sigma Y is yielding stress or proof stress. The second, FLP, this is the non-proportionality, which mentioned so many people here mentioned about this. And I equated like this equation. This is very simple. The equation I is the unit vector into the reference axis, and the equation R is this unit vector at time t at each principal direction at each time. And this cross is outer product, and the L pass. So L pass is the full length all loading pass. DS with this integral means line integration using the loading pass. So in this case, even though this Guzai is constant, and we rotate around the reference axis, in that case, the proportionality also increase, even though this angle is constant. So this is the correlation of the failure life using the GC equation, employing this non-proportionality. And this is the experimental data. This is the calculated the failure life. This is the material employed here. So some scatter can be seen, but we could get a relatively good correlation. So, in the constant loading is okay. How to evaluate in the random loading? So, this is the example of the random loading. So, even though the complicated loading, if we use the IS method, we can figure out a very simple loading path, similar to the uniaxial loading. So this means that once we got this waveform, we can calculate the counting, cycle counting, and each amplitude. So I mean we can separate the loading paths. For example, using the rainfall method. Okay. So this is my idea how to evaluate the failure life under proportional loading. So at each the waveform, we can calculate the range, the stress over strain range, and mean value, and also FLP at each waveform. And after that, we can obtain from the failure life at each amplitude of stress over strain using the Excel curve from the Excel curve of the uniaxial tension compression test. Of course, in that case, we use the GC equation and FLP. And finally, we use some damage model like linear figurative damage group. Finally we can obtain the failure life precisely. Okay, next I will show the visualization of the stress over strain and multi-axiality. So we can. So this is an example of the input data. We can. This is the time, and so we can obtain the 6 component of stress strain as a function type. Then we input this data. So in the beginning, we can show the stress or strain waveform of the 6 component like this. This is the input data, and using the IS method, we can obtain the polar figure of the stress or strain path like this. So in that case, the reference axis is determined in this direction. However, so you can also choose the reference axis. So in that case, we drag this picture is not clear. We drag this picture and we can rotate. So we can change the direction of view, and then we can find some critical view as you like. So, for example, this is the same T stress strain path. We can rotate, and we can find some critical direction from here. And then finally, we can get the stress amplitude here, and this hatching area means intensity degree of non-proportionality at each time. This height means non-proportionality at this time. So we can know the stress over strain amplitude and the non-proportionality simultaneously using from this picture. So this picture is very roughly showing the meaning of the stress amplitude and non-proportionality. This is the example for the butterfly path. This is the path in the polar here. So the projection onto this red cylinder. So this projection means the stress over strain amplitude. And the projection in the bottom side, this means the degree of the non-proportional. So from this picture, so researcher and the engineer can know how much, how is the stress amplitude, how much the non-proportionality is. Okay, I must go very quickly. This is the final picture. This is an example of the calculation. This is the data experiment data. And this is the data from the low carbon steel, maybe the SS40, maybe I don't remember. So this is the one example. We calculate this is the polar figure of this from this the waveform. So as you see that this is the straight line, no whites. So this is the proportional loading. Okay. In that this time, this is very complicated loading. So and also I evaluate the failure line, this comparative failure line. This is the experimental, this is calculated. This is the number of blocks of the random loading. So this is very close relation. And also, this is the small number of blocks, 7. Experimental number is the 7, we calculated the 10. I guess that this is not so big difference. Okay, this is the conclusion. I must skip due to the time of blank. So now I have a question. It is rather my request. So I have many data in the multi-axial loading, in the tension and the torsion, and the tension, torsion with inner pressure, and equibiaxial tension using the two-smoke specimen, and the triaxial using the triaxial specimen. However, I don't have any data in the triaxial stress state with rotation of principal stress strength. I have never seen that kind of data. So if you know, please show me. This is my request. Thank you for your attention.